Hi, my name is Keval and today I am going to present our work on fast unsupervised anomaly detection in traffic videos. Anomaly detection in general is a vast, crucial and challenging research topic which deals with the identification of data instances deviating from nominal patterns. Video anomaly detection plays a very important role in ensuring safety, security, and prevention of potential catastrophes. Events such as traffic accidents, robbery, and fire in remote places require immediate counteractions to be taken in a timely manner, which can be facilitated by the real time detection of anomalous events. Despite its importance, a very limited body of research has focused on online and real time detection methods. Also, due to the exponential increase in number of CCTV cameras, manual surveillance has now become nearly impossible. Now let's take a look at why video anomaly detection is such a challenging problem. For complex applications such as video surveillance, what can be considered as nominal or anomalous is contextual, and hence exact notions of nominal and anomalous behaviors are difficult to define. For example, a stopped car at a traffic signal is nominal. However, on a highway, the same behavior would be considered anomalous. Secondly, sufficient training data might not always be available, so the proposed solution should be able to generalize well to different situations. Recent deep learning based approaches perform well on benchmark datasets but cannot generalize well to unseen scenarios, and also they have several shortcomings in terms of interpretability and reliability of their decisions. Moreover, CCTV cameras are edge devices which have limited computational and storage capacity, so computationally expensive models might not be feasible to implement. Hence, we propose a transfer learning based approach using k-means clustering to tackle this problem. By using transfer learning, we efficiently remove the need for training data, and by using statistical decision making, we make the model computationally less expensive. Now, let's take a look at the proposed approach in detail. The purpose of this challenge was to design a practical framework which is capable of detecting anomalies in traffic videos. Our proposed approach is divided into three parts. First, pre-processing, which includes background modeling, extracting the road segments, and detecting the vehicles. The second is candidate selection, which includes a k-nearest neighbor based approach to remove outliers and a k-means clustering approach to select potential candidates. Finally, the third part consists of defining the region of interest and a backtracking algorithm to find the time when the anomaly begins. We now explain each module in detail. While most existing algorithms also employ some form of object detection, they train specialized models on huge datasets. While such frameworks perform well on the benchmark dataset, we believe that it is a very specific approach and would not be practical because of the immense computation cost associated with retraining such models on new data and the time required to make a decision per observed frame. As we know, computationally heavy deep learning based models fail to learn continuously as new samples arrive. Hence, to this end, we propose leveraging transfer learning to detect objects using a real-time object detection system such as you only look once, YOLO, pre-trained on the MS COCO dataset to obtain the location of potential anomalies. In the pre-processing pipeline, using the video frames, we first remove the moving vehicles by background modeling. Then we divide the frame into 3 overlapping parts in order to keep it consistent with the trained YOLO model. This is passed through the YOLO object detector, which returns bounding boxes of stopped objects in the frame. We also extract segmentation maps to remove objects detected in the background. The bounding boxes are then passed to the second stage, where we use a nearest neighbor based approach to rule out objects that are misclassified by the object detector. While setting a low threshold of confidence for object detection helps in detecting very small objects, it also leads to misclassification of objects in the background like traffic signals and road signs. Also, while the background model suppresses most of the moving vehicles, some slow moving objects are not completely removed and they get detected by the detection algorithm. By observing a single frame, it is very difficult, if not impossible, to remove such misclassifications without leveraging external datasets. However, by including the temporal information, that is, by combining all the bounding boxes detected in the video, we see some patterns emerge. The objects in the background which are misclassified tend to occur frequently at the same location from the beginning of the video till the very end and form a high density cluster. Conversely, the slow moving objects do not occur frequently at the same location and thus they look like outliers. Hence, we implement a nearest neighbor based approach to rule out such cases. Following the nearest neighbor implementation, we employ a k-means clustering algorithm with a segmentation map overlay to localize potential hotspots, that is, locate regions where stationary objects were detected. This step provides us with k-centroids or potential spatial locations in the video where an anomaly might have occurred. Then we iteratively look for the first time where we detect an object at each of the k locations or potential regions of interest. On the right, we see 3 images from the same test video for different regions of interest. All the images represent different time instances and could be for the same or different vehicles. In the final stage, we backtrack from each individual time instance while comparing the structural similarity for each location. Ideally, when there is no stalled vehicle at the location, the structural similarity is very low and almost close to zero. As soon as a stalled vehicle appears in the frame, there is a dramatic increase in the structural similarity, which we detect by setting a threshold on the similarity statistic. Structural similarity is a perception-based model that considers image degradation as perceived change in the structural information. To remove increases caused due to noise, we apply a Savitzky-Golay filter to the similarity statistic. Specifically, we focus on whether the increase is persistent over several frames or occur only over a couple of frames. Finally, the first instance at which the statistic crosses the decision threshold at any of the regions is declared the anomaly onset time. Again, on the right, we see the statistic for each region of interest. In the first case, there is a sharp increase, but it is not persistent. The other 2 increases are persistent over several frames, but since the increase happens first, in the third case, we select the instance as the onset time of the anomaly. If no anomaly is present as seen in the first case, there will be no persistent increase over several frames. The evaluation metric is given by the S4 score, which is the F1 score multiplied by 1 minus the normalized root mean square error. The F1 score is given by 2 times precision times recall divided by the precision plus recall. The F1 score measures the detection accuracy and false alarm performance, while the normalized root mean square error measures how well the anomaly starting time is determined. The maximum S4 score that can be achieved is 1 for an F1 score of 1 and a normalized root mean square error of 0. The track 4 of the NVIDIA AI City Challenge 2020 consisted of 100 training videos and 100 testing videos. The average video length was about 15 minutes and had a frame rate of 30 frames per second. The resolution was 800 x 410. The anomalous behaviors mainly constitute of vehicles driving off the road, stalled vehicles, and crashes. However, due to many factors such as a range of weather conditions, lighting conditions, viewing angles, etc., each video presents a unique challenge. The main objective of the task is to detect the anomalies in videos with a low detection delay and a high F1 score. As compared to previous year challenges, this task is considerably more difficult as no external dataset was allowed. Here we present our results. We achieved the second rank with a S4 score of 0.6625. Our F1 score was 0.7273 and the RMSE score was 26.7348. The first rank was achieved by Baidu with a S4 score of 0.9695. In this work, we attempted to tackle the anomaly detection in traffic video challenge. For video anomaly detection, we presented a fast algorithm which consists of a deep learning based object detection module and 2 statistical decision making modules. We show that as compared to the other state of the art methods, we have negligible training computational overhead, and we are also able to generalize well to different scenarios without access to any external data. By leveraging the statistical aspect of the proposed algorithm, in the future we aim on providing performance analysis such as upper bound on the false alarm rate. We would also like to include density estimation for the k-means algorithm and a continual learning based model which would be capable of learning different type of anomalies. We would like to take a moment to thank the organizers of the NVIDIA AI City Challenge 2020 for such a smooth experience. Thank you.